So after looking at the reactivity series, the next unit we're going to look at is the extraction and uses of metals, which is actually in a way linked to the reactivity series we've just studied. So these are the learning objectives. There are 6 learning objectives. Know that most of the world's metals are extracted from ores. Explain how they are extracted. Be able to comment on these extraction processes. So we'll actually go into depth with a couple of examples. Explain the uses of aluminium, copper, iron and steel in terms of their properties. Know that an alloy is a mixture of a metal and one or more elements, and explain why alloys are harder than pure metals. So first things first, let's see where we get our metals from. We get them from ores. So most metals are actually found in rocks and in the form of an ore. So essentially these are compounds that are chemically bonded to other elements. Obviously the higher you get up on the reactivity series, the more likely that you will find the metals in the ores, whereas you go further down, they're less reactive, so most likely found in their native form. This is where the reactivity series is introduced again. So you have basically platinum at the bottom, hydrogen kind of in the middle. So platinum, gold and silver, because they're low down, aren't very reactive, so they're usually found in their native form. So they don't necessarily have to be extracted, they have to be mined. Okay, so you can mine for silver, gold and copper and platinum because they don't actually react and form compounds. Whereas things like lead, iron and zinc, they usually are formed from reduction, usually reduction using carbon or coke or charcoal, and we'll look at iron as an example of that. And finally, the highly reactive metals are probably going to be extracted by electrolysis because they're found obviously in these ionic salts primarily. And we're going to look at one example in the form of aluminium. The first one is the extraction using carbon. We're going to use the example of iron. But metals such as zinc, iron and copper are present usually as their oxides, okay? Iron oxide, copper oxide and zinc oxide. So what you do is you basically heat the oxides with carbon to essentially obtain the metal which melts out. So for example, if we need zinc, we first obtain it from zinc sulfide or zinc ore in the form of either the sulfide or the oxide. We react basically the zinc sulfide with oxygen, and this forms zinc oxide and sulfur dioxide, and that's the equation there. And then what happens is the zinc oxide is further reduced with carbon in a furnace under high temperatures. Okay, so basically what you do is you react the zinc oxide with carbon monoxide as the carbon source. It forms zinc metal and the carbon dioxide, which can be removed as a gas, obviously. And there's the equation. Or you can allow zinc to undergo electrolysis, which is a little bit more complex and a little bit more complicated, so it tends to be extracted using carbon. Okay, and we've already looked at that, so that's basically when zinc ions gain electrons, so they're reduced down to zinc metals. Okay, and of course zinc metal is used to galvanize iron, which we've looked at previously. It's used in sacrificial protection as well, and made to use combined with copper, especially to make alloys, and also to make batteries. So that's the uses of the zinc metal.
Steel is the most important metal in the world, with an annual production of about 750 million tons. Different steels are used in a wide range of products. Steels are fundamental to transport. Steel is one of the basic building materials, both for interior and exterior use. Blast furnaces producing iron and the basic oxygen process for steel making operate at 4 British steel plants in the UK: Scunthorpe, Redcar, Llanwern and Port Talbot. We shall concentrate on the Scunthorpe site. Raw materials are brought to the port of Immingham. Materials can also be transported through the motorway and rail networks. The principle of iron and steel production is that iron is extracted from its ores by heating with coke and limestone in a blast furnace. Molten iron then becomes the raw material for producing steel in the basic oxygen steelmaking process. On the Scunthorpe site, iron is extracted from its ores in these 4 blast furnaces. Coke is made in ovens here. Sintering, that is blending iron ore, coke and limestone, takes place here. Iron is converted to steel in the basic oxygen process in this plant. And finished materials are converted into a variety of shapes here. The essential raw materials for making iron are iron ores, coal and limestone. Iron ores are imported from Australia, Canada and South America. Limestone is quarried in the UK and is delivered to Scunthorpe by road. Coal is imported. The coal is converted to coke by heating for 18 hours in an oven. Gases, tar and ammonia are driven off, leaving an impure form of carbon. The ore, coke and limestone are blended in this ore bed. They are crushed and heated together to form sinter. Sinter will not collapse in the furnace. It has a large surface area to speed up reactions. Sinter and extra coke, ore and limestone, known as the charge, are lifted to the top of the blast furnace. The Scunthorpe furnaces are fed by skips. Furnaces run continuously day and night. The blast furnace is a steel tower up to 40 metres high, lined with heat-resistant brick. The charge is delivered into the top of the furnace. Hot air is blown in at the bottom. Molten iron is produced and slag. Coke burns, producing heat and carbon monoxide. The carbon monoxide reduces the iron oxide in the ore to molten iron. Limestone, calcium carbonate, decomposes to calcium oxide. This reacts with the sandy impurities in the ore to give molten slag, mostly calcium silicate. The blast furnace reactions are maintained by blowing hot air into the base of the furnace. Between 10 and 20 times a day, the molten iron, called hot metal, is tapped into torpedo ladles. Torpedo ladles hold 300 tons of molten iron. Molten slag floats on top of the iron and is tapped along with it. The slag cools and solidifies. It can be used in cement and for road building. At this stage, the molten iron contains around 4% carbon and other impurities. The iron is brittle. Steelmaking improves the properties of iron. In the basic oxygen steelmaking process, the BOS process, a converter is partly charged with solid steel scrap. Hot metal from the blast furnace makes up 3/4 of the charge. A high-speed jet of oxygen is injected onto the molten iron, and lime, calcium oxide, is added. The oxygen converts the impurities into their oxides. The main effect is to reduce the percentage of carbon. Carbon monoxide is collected for use as a fuel. The other oxides react with lime to produce slag. Molten metal is drawn off through a tap hole. After further treatment, the steel is solidified. One method is to use moulds to form steel ingots. A more recent method is continuous casting, where steel is poured through cooled copper moulds and drawn downwards by rollers. The resulting steel shape is cut into lengths. Rolling the steel produces the finished shapes required.
So another example is the blast furnace for extracting iron. So there's the diagram there. I won't go through it in great detail because we're going to go through in step by step in the next few slides. But essentially what happens is that iron ore, iron oxide, is basically heated at very high temperatures and about 500 degrees Celsius. And essentially what happens is the carbon reacts with the iron ore to form basically carbon monoxide, which reacts with the iron ore to produce iron metal, which can be basically melted off at the bottom because it will sink, and the carbon dioxide obviously comes off as a gas. In terms of the individual reactions, the first step, carbon reacts with the oxygen in the now superheated air to make carbon dioxide, and is indeed the carbon dioxide which then further reacts with the carbon which is being basically dumped into the top of the blast furnace to form carbon monoxide. So this carbon monoxide formed then acts as a reducing agent and reduces the iron oxide to iron. Okay, so the iron 3+, which is present in the iron oxide, iron 3+, basically gains this time 3 electrons from the carbon monoxide to form the associated iron. Okay, so it's actually basically being reduced from iron 3+ to iron by the carbon monoxide. Then the final steps are about impurities. So calcium carbonate reacts with the silicon dioxide impurities present in the iron to make something called slag, okay, which is this kind of formula here, which drops down and can be extracted because it's not as dense as the molten iron. So let's now look at the relationship between iron and steel. So the atoms of pure iron are arranged in a regular way that lets layers of atoms slide over each other, which makes it pretty much too soft. Okay, so you can see here that in normal metallic iron, the atoms can slide over each other, and that means that iron itself is too soft and it can't really be used to build bridges or motor vehicles because it's not strong enough. And iron from the blast surface is actually an alloy, and we'll look at alloys further on. Essentially an alloy is a mixture of a metal with another element, and in this particular case the element is carbon. So it's hard but very brittle to the touch. So what you have to do is you basically have to convert iron into steel, you have to remove some of the carbon. Okay, and the way that's done is basically by heating it, so it's an oxygen, so you've got carbon converting into carbon dioxide. And here's some examples here of what they're used for. So low carbon steel, which is about 0.25% carbon, is easily shaped and used for car bodies. High carbon steel, which is closer to the stuff that comes out of the blast furnace, is hard but slightly brittle, so it's used for cutting tools. And stainless steel is actually an alloy or a mixture of chromium and nickel with iron, which resists corrosion and is used in cutlery and sinks. So as said, the carbon is removed by blowing oxygen into the molten metal. The carbon reacts with the oxygen to form carbon dioxide. Okay, so you've just basically got carbon plus oxygen reacting to form carbon dioxide, which of course is a gas. Okay, and it can basically escape into the atmosphere. So that's the example of using carbon to reduce a metal, because iron sits kind of in the middle of the reactivity series. But for more reactive metals like aluminium, which form very strong bonds with oxygen in the form of aluminium oxide, we use electrolysis. So aluminium is usually found in bauxite, which is aluminium oxide, and electrolysis is the technique which breaks down the aluminium oxide into aluminium and oxygen. So electrolysis is breaking down compounds using electricity. Now the melting point, because the bonds are quite strong in the aluminium oxide of bauxite, is 2000 degrees. So what happens is they add a chemical called cryolite, and this reduces it to about 1000 degrees Celsius, and it reduces the amount of energy required in terms of electricity to melt the associated bauxite. So what are the reduction and oxidation half equations of the extraction of aluminium? Okay, we're going to look at that now in the next slide.
And its alloys are among the most important metals in everyday life. They resist the effects of other chemicals, are strong yet flexible, and are light in weight. Aluminium is the third most common element in the Earth's crust. It is extracted from its oxide by electrolysis. About 135,000 tonnes of aluminium per year are extracted at Anglesey Aluminium in Holyhead. This is about half the UK total. Anglesey Aluminium has its own deep water port for importing raw materials. Aluminium can be shipped out by road, rail or sea. The site is really 3 plants in one. Electrolysis takes place in 4 covered areas, each half a kilometre in length and each containing 78 electrolysis cells. The aluminium is alloyed and cast in the metal finishing shops. Anodes for the process are produced here. Aluminium oxide, often called alumina, is stored here, fed by an underground conveyor belt from the docks. This white powder is alumina. The aluminium is extracted from it. Alumina is imported from Jamaica, Ireland and Spain, where it's been purified from bauxite ore. This is one of the 4 rows of electrolysis cells called pot lines, where the electrolysis takes place. The current to the pot lines is about 157,000 amps at 4.5 volts. Anglesey Aluminium takes electricity from the national grid. This is one of the 312 cells in the pot lines. The electrolysis cell consists of a rectangular steel shell lined with heat-resistant brick and then carbon. Each cell is filled with molten cryolite. The aluminium oxide is dissolved in molten cryolite so that it conducts electricity. 18 carbon anodes dip into the electrolyte. During the electrolysis, aluminium ions move to the cathode, gain electrons and become aluminium metal. Oxide ions move to the anode, where each ion loses 2 electrons and the atoms pair up to become oxygen molecules. These are the chemical equations. As the electrolysis proceeds, the aluminium oxide is decomposed into aluminium and oxygen. A crust forms on the electrolyte, and this has to be broken to feed in new aluminium oxide. This happens every 3 to 4 minutes. The hoppers on the cells are filled from an overhead ore bucket every 16 hours. The electrolyte is at about 955 degrees Celsius. At this temperature, the carbon anodes gradually burn away in the oxygen from the electrolysis. Eventually, the anodes have to be replaced, and this happens every 28 days or so. The remaining carbon is broken off the old anodes, crushed, mixed with new coke and pitch, and pressed into shape. The newly pressed anodes are baked for about 24 hours in gas-heated pits. This produces electrodes which will conduct electricity and not crumble away in the cells. The temperature of the pit is important and is checked on a regular basis. The baked anodes are fitted onto steel stubs. These are held in place and connected electrically with cast iron. The anodes are sprayed with molten aluminium to protect the top and sides. Electrolysis takes place 24 hours a day, 365 days a year. A loss of power of more than a couple of hours would be disastrous, as the electrolyte and the aluminium would solidify. Liquid aluminium is sucked from the cell into a brick-lined steel crucible. Each cell produces about 50 kilograms of aluminium per hour. Some of the aluminium is cast as almost pure metal. Some is made into alloys by adding other metals. This metal being added is magnesium. Aluminium alloys or pure metal can be cast into different shapes. The liquid metals are poured into moulds where they solidify and can be lifted out. Aluminium metal is sold in various shapes according to the needs of the customer.
So aluminium ore, as we've just seen from the previous slide, is bauxite, which is purified to yield a white powder, which is known as aluminium oxide. Okay, and the formula for aluminium oxide, of course, you should know, is Al2O3. And the extraction process is done by electrolysis. Okay, and electrolysis is basically the concept of splitting by electricity. Okay, electricity, lysis, to cut. So the aluminium oxide must be melted so electricity can actually pass through it, and this is done by dissolving it in molten cryolite, because solid aluminium oxide will not conduct electricity, because obviously all the electrons are used in the bonds. There's no free electrons to move around, which is required for electricity. So the first thing to do is melt it. Okay, and there's the diagram there of what's actually happening. You've got your graphite anodes, okay, because graphite carbon's not very reactive, and you've got purified aluminium ore dissolved in molten cryolite as a liquid, okay, all around here. Okay, it's all dissolved aluminium ore and cryolite. And you've got the molten aluminium basically falling to the bottom as the electrolysis process occurs. So the negative electrode and positive electrode are made of graphite due to their lack of reactivity. The aluminium formed at the negative electrodes aluminium forms at the negative electrodes, which you can see here. Okay, forms here and then drops down where it is collected. And this is the equation. The aluminium ion gains electrons to form aluminium, so it's reduced, and oxygen forms on the positive electrodes, okay, these ones here, okay, where the oxide anion loses electrons to become oxygen, which is of course known as oxidation. It's losing electrons. The oxygen reacts with the carbon of the positive electrodes, forming carbon dioxide, so that means that the graphite anodes have to be changed ever so often as they kind of react with the oxygen. So that's just a task we'll be doing in class called sit up or sit down. I won't go further into it. We'll do it in class, no problem. Okay, so the final thing we're going to look at is the idea of alloys. Okay, so for example, what happened if Silver Surfer and Iron Man joined forces? They'd be alloys. Okay, so an alloy, as we've already kind of touched on, is a material composed of two or more metals, or a metal and a non-metal. So the example of iron and carbon, for example, for different forms of steel. An alloy made by a single solid of elements and a mixture of metals, or an intermetallic compound with no distinct boundary between metals. So what does that mean? So it essentially just says it's a mixture of metals where there's not one section that's like iron and one section that's copper. It's all intermixed together. Yep. So an intermetallic compound has one or other alloy and pure metal embedded within it. So it's all mixed up. Okay. There's not one part that's one metal and the other part that's the other metal. There's the example there. Don't have to know this in great detail, but you have either interstitial or substitutional alloys. Okay, so if substitutional, an element replaces host atoms or the other other metal in an ordered arrangement. Or the other way you could do it is you have one metal and the other metal kind of fits in the gaps, which is known as interstitial. Or that could also be carbon, for example, in the case of steel. And alloys are used where there are appropriate properties are superior to those of the pure component elements for a given application, which moves us on to the last slide, the properties of alloys and what metals are used for. Okay, so here's an example here. Bronze, its properties are hard and strong, doesn't corrode. It's made of copper and tin. Brass, copper and zinc, harder than copper due to the zinc. Steel, we've already looked at that, it's hard and strong due to the little bit of carbon in there. Stainless steel, a combination of those particular metals, means it has the properties of being strong and shiny. And duralumin, aluminium and copper, used to be light and strong. And pewter, combination of 96% tin, 3% copper. Okay, luster, shiny and strong. As opposed to the different kind of metals, so for example, copper is used for wiring. Okay, because it's a very good conductor of electricity. Okay, we've already looked at iron and what it's possibly used for. Aluminium, you'd use that for lightweight bikes and things if you're doing triathlons. Okay, very lightweight metal but quite strong. Okay, and the other example that you'd probably be asked to look at, something possibly around zinc itself. Okay, so again, zinc could be used for kind of galvanization and other similar properties, which we've already looked at in the earlier topics around reactivity series. And that's pretty much all you need to know for the ideas behind the extraction of metals.